Hi, class. So this is our second lecture on Introduction to Organic. And in this lecture, it's going to be a lot shorter, much shorter than the last one. But I'm going to go over on how to draw and recognize organic compounds. We have a worksheet. It's worksheet 36B, and it's just drawing organic structures and looking at the different ways we represent organic compounds. So the reason why we do this is, previously when we wrote structures in inorganic chemistry, we drew Lewis structures that showed all the bonds and all the atoms. And in organic chemistry, that's a pretty tedious way to draw structures of organic compounds because they're very big. So there are shortcuts that we take in drawing the structures and some assumptions we make when you look at those structures. So that's what I'm going to go over today. So I'm going to switch to my camera, so that'll be ready to go when we do the worksheet. And I'll screen share now, and it's a nice short slideshow. So I think there's only 9 slides in this. Anyway, this is these structures are shown in chapter 20.1. So as you read through chapter 20.1, you'll see these different ways that organic compounds are drawn. So previously, as I said, we learned how to draw Lewis structures, which shows all the bonds between the atoms. In this short lecture, we'll also look at how we draw organic compounds in condensed structures. And then lastly, the skeletal structure. And if you remember in the first lecture, I talked about how carbon atoms provide a skeleton for the organic compounds and other elements attached to that carbon skeleton. Well, there's a really shorthand way, I call it the zigzag structure, or the line angle structure. We just draw it's kind of like a stick figure of the carbon skeleton. And then from that, you would attach the other atoms that we talked about previously. Oxygen and nitrogen are pretty common, but the skeletal structure doesn't show the carbons or the hydrogens. So it's just a skeleton. And you'll see what I mean as we get to that part. So the second objective is to be able to recognize and convert structures from one to the other, and we'll be doing that on the worksheet. And lastly, be able to recognize the molecular formula. So remember, the molecular formula only shows the numbers of atoms that are in a molecule. And lastly, we'll be doing worksheet 36B to practice some of these objectives. Okay, let's see, here we go. Oops, went a little too far. Okay, so just to review before we start drawing chemical structures of organic compounds, remember carbon makes 4 bonds. It's a tetravalent, so the bonds can be single, double, or triple bonds. It can bond to itself to make chains, branched rings, and we'll be looking at some of those. Especially in the next chapter, we'll look at isomers. And so lots of isomers, if you remember from chapter 19, are compounds that have the same molecular formula but a different structure. And see a few other points about drawing structures. Carbons makes only single bonds to hydrogens and to halogens. And then it can make single, double, or triple bonds to the other carbons and also to other elements like oxygen, nitrogen, sulfur, and phosphorus. Next. I'm not sure what's going on here. So remember a few other things too. All carbons are carbons are tetrahedral. Oh, wait, There's something up here. We're talking about alkanes. So if you remember last time, alkanes are hydrocarbons with only single bonds. Remember, a hydrocarbon is an organic compound that only contains carbon and hydrogen, and that alkanes are one type of hydrocarbon that only have single bonds, and alkanes are actually a family. So we're going to talk about families later on, but alkane is a kind of family, and it's a family of organic compounds that only contain carbon and hydrogen. So since all the carbon atoms only contain single bonds, that means all the carbon atoms in alkanes are tetrahedral. Remember from the last lecture, a tetrahedral carbon contains only contains sp3 hybrid orbitals that are used for bonding to make these single bonds. So because all the carbons contain single bonds, it's called a saturated molecule. So the alkane hydrocarbons are saturated, and you can think of it as being saturated with hydrogen. You can't add any more carbon-hydrogen bonds to the molecule. When alkane has 4 or more carbon atoms can be arranged so that you can get a branch, or and depending on how many carbons, the more carbon atoms you have, the more branches you can have. And there's some examples of some of these Lewis structures below. So remember, I talked about the carbon skeleton can be linear, it can be branched, or it can be cyclic. And so we're going to see all of these examples as we go through this chapter. The one thing about alkanes, since they're saturated hydrocarbons, the generic formula is Cn, where N is the number of carbons, H2N plus 2. So we will see that as we go through also. That's an important formula to remember because it applies to all alkanes. And if you remember last time we looked at the simplest alkane was methane, it was CH4. And you can if N is equal to 1, it would be the formula becomes CH4. So here is an example of a linear alkane on the bottom and 2 branched alkanes. So it turns out this is a C5H10. I don't know if I've written that someplace. I'll write it here. So this is a C5, let's see, whoops, C5H10 or CnH2n plus 2. These are all C5H10. So the first one is a linear. I don't know if you saw the little red line, but this is called the linear molecule. So that's where all the carbons are joined in a line, straight line. Okay, they're all connected one after the other, kind of a bead, if you will, of carbon atoms. Okay, so that's one way you can arrange, or you can bond these 5 carbon atoms together. The second way is with a branch. And in this case, you have a 1 carbon branch. And we've got a straight chain of 4 carbons now, 1. So we have, let's see, we have 1, 2, 3, 4 carbons in that chain, and there's a 1 carbon branch off of it. But the molecular formula is still C5H10. And lastly, we have another branched molecule. We have another branched molecule that has 3 carbons in a row and 2 1 carbon branches off of that. So that's a third way we can bond these 5 carbons together. Just as a preview, these are isomers. We call these structural isomers, and we'll get into structural isomerism in the next lecture. So these are all Lewis structures. But you know, when you have to draw these, it's pretty tedious. Like if I was going to draw this, I'd have to do carbon, 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 until I have 5 carbons in a row. Then I have to draw all these other bonds. And then I have to add hydrogen to it. You know, you're probably getting pretty bored with this, and I'm getting that. So I'm going to, well, I guess I'll finish since I started. So a C5H10 is a pretty small molecule, and that's pretty tedious just to write that. So let's see what else we can do. Oh, but before we go on that, we talked about carbon can be arranged in a straight line, which is called linear. They can all be connected together, one after the other. That's called a linear skeleton, if you will. We said there's branch skeletons. There's also cyclic skeletons. And the smallest cyclic skeleton, to make a ring, is 3 carbons. You can have multiple rings. So you can have rings connected together, or you can have what's called fused rings. So we can have, I don't know what they call it if they're connected. There must be a name for it, but I'll draw a picture. But the other kind of ring you can have when you have more than one is called fused rings, where the rings join along one side. I'll give you an example of those. So when you have a cycloalkane, remember being an alkane, all the carbons have single bonds, but because you form a ring, you have to take away 2 hydrogens. So the generic formula for a cycloalkane is CnHn. So the, nope, that's a mistake. It's CnH2n. CnH2n is the formula for cycloalkanes. So previously we had CnH2n plus 2. You take away those 2, and you form a ring. This also happens to be the generic formula for the class of compounds called hydrocarbon alkenes. We'll get to those in a bit. So when you name these cycloalkanes, we're not going to spend too much time on naming, but you just put cyclo in front of the name. So the number of carbons is kind of the root name. So propane, everybody's heard of propane. That's what we have in our heat our homes with. This is the molecule that are in your propane tanks. So it's a CH3, CH2, CH3. I've bent it here because remember it's tetrahedral. Every carbon is an sp3 hybridized. The shape is tetrahedral. So every carbon has a 3-dimensional arrangement of bonds around it. So drawing it in a bent structure kind of illustrates that. Well, if we take away 2 hydrogens, so let me just take away 2 hydrogens. It means let me put a 2 here, and I'll put a 2 here. That means those 2 carbons on the end only have 3 bonds, so they each have to have 1 more bond. So we can put another bond here. When we do that, we end up with this ring structure called cyclopropane. And you can see the formulas have changed. We have a C3H8 on the left and a C3H6 on the right. So I think the next slide shows a bunch of other cycloalkanes. Now the little note here at the bottom says these are called condensed structures. So if you remember in the last slide, the last slide showed Lewis structures, which showed all the bonds. Well, condensed structures only show the carbon-carbon bonds. The CH bonds are condensed. So that's a kind of a quick way of drawing organic structures. So condensed structures are very common. That's a common way to look at and see an organic molecule drawn. And then you have to know, because they're all single bonds, what you have to understand with the condensed structure is that the CH bonds are all single bonds. You have to remember that. And if you wanted to, if you needed to know what the 3-dimensional structure is, you know that each carbon is sp3, so it's a tetrahedral. So each carbon is a tetrahedral. And all the carbon-hydrogen bonds are single. And in fact, all the bonds in alkanes are single bonds. I keep repeating that so you can remember it. Okay, so what's next? Okay, there we go. So here's some other common cycloalkanes. So the one we just looked at is here over the left with N, the number of carbons, N equals 3. And then we have N can equal 4. That's called cyclobutane and cyclopentane and cyclohexane. You don't have to remember the names. This first row shows the kind of a model, picture of a model. It's a balanced model, which are commonly used models that's used to look at structures of organic compounds. In this row down here, we have the condensed structures that I showed you before. And in the last row, we have, this is called the line angle or the skeletal structure. So this is the skeletal down here. The skeletal structure at the bottom. And in the skeletal structure, you don't show the carbons and you don't show the hydrogen bonds or the hydrogen. You just show the bonds between the carbons. Now, if we had another atom in there, like an oxygen, you have to show the oxygen. Because if you don't show an atom, the assumption is when you look at a structure that it's carbon. So you can see how each of these cyclic alkanes look when you draw a skeletal structure. Well, the skeletal structures are really easy to draw and quick to draw. So compared to both the condensed structure or the Lewis structure. I wanted to write the formulas of each of these. So this first one is C3H6. The second one is C4H8. And the fifth one is C5H10. And the last one is C6H12. And I don't have to count the hydrogens because I have to count the carbons, but I don't have to count the hydrogens because I know these are cycloalkanes and the generic formula is CnH2n. Okay, kind of sure if you can remember those things. So these formulas are good to write down, to put down in your notes. And I'm not sure why, but I have trouble going from slide to slide. Okay. Lastly, I want to look at all three of these structures together. So this slide shows the molecular formula on the left, and then the condensed structure on the right. And this is a C3H8. And then the Lewis structure. And then lastly, the skeletal structure. So this is not a cycloalkane. This is a linear alkane or open chain. You could say not a cyclic alkane. So the formula, generic formula for not a cycloalkane is CnH2n plus 2. So that's shown there. That fits the C3H8. The first structure is a straight chain, and that's the only way you can connect carbon atoms if you only have 3 carbon atoms. You can't make a branch. So I don't know if I have another. I think that's in the next slide when we talk about isomers, but I could bend this one down here, put a CH3 down here. So if I put it down there, but it's still 3 carbons connected in a row. It's still the same molecule. I haven't changed it. I've drawn it differently, but it's still the same. It's just like this first structure, the second Lewis structure, and the third skeletal structure. They're all drawn differently, but they're all the same molecule. The skeletal structure, because we have 3 carbons, you have to show a bend. Wherever there's a carbon, an angle like this in the middle, that represents a CH2. Wherever there's the end of a line, the terminus, if you will, the end is always a CH3. We have two ends whenever you have a chain or anything. You have at least two ends whenever you draw a molecule. If it's a straight chain, you have two ends. If it's a branch chain, you'll have multiple ends. And wherever there's an end of a line, it's a CH3. Okay, that's what that means. It says, the little note at the bottom says atoms are listed left to right in condensed structures, but they don't have to be. You could put H3C there. You could put the H in front of the carbon. In the skeletal structure, if we had an oxygen in here, we'd have to write the oxygen. And if there were hydrogens attached to the oxygen, like an OH, you'd have to write that. Okay, in condensed structural formulas, it shows how you do, sometimes they're called the expanded instead of the Lewis. So the expanded CH3 is shown like on the left, and condensed CH3 and condensed CH2. But there is a shortcut. Let me see if we show that. So this is a skeletal structure formula, and this is a bigger molecule. So this one has, let's see how many carbon atoms there are. So the slide says line angle, but it's also the skeletal. I think the book calls these skeletal structures. Write that up here. Oops. The skeletal structure. And like we said previously, the end is always a CH3. Wherever there's an angle, it's a CH2. The bonds are just showing the connection between the carbons. So this molecule is a CH3, CH2, 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 CH3. And if I ask you to draw the condensed structure, you draw this. You draw CH2 or CH3, and then 1, 2, 3, 4 CH2s. 1, 2, 3, oops, CH2, 1, 2, 3, and then another CH2. And then at the end is a CH3. Okay, so that's the condensed structure. Notice in this condensed structure, I didn't put the bonds between the carbons. That's okay, you don't have to. So we could include the bond. Oops, you can include these little bonds, but you don't have to include the bond. But you can do a shortcut. Since we have all these CH2s in a row, we can just write this as CH3, and this helps, CH2. And then there's 1, 2, 3, 4 of those, CH3. So that's a much faster way of writing the condensed structure. And you can do that if it's just a straight chain. But that's what that means if you see something written that way. What's the formula? This is an alkane. We're talking about alkanes now. So we know there's 1, 2, 3, 4, 5, 6. So I know this is the formula is CnH2n plus 2. So it's C6H14. Okay, and I don't have to count the hydrogens to know that. Lastly, so this shows a different alkane. This is the C5H12, and we have the expanded structure on the top, the condensed structure in the middle, and the skeletal structure at the bottom. And so that's it for this lecture. I'm going to flip over to the worksheet now. So I'll stop my share. And we'll go straight to the worksheet, which is shown here. So on the front of this worksheet is the front page tells all the rules for drawing structures. And it talks about Lewis structures, then it talks about condensed structures, and lastly, line structures. So I'm not going to go over these rules. We've talked about many of them in the lecture part. So I'm just going to go straight to the worksheet, to the problems that we have on this worksheet. I would suggest keeping that the rules for drawing structures handy as you go through and do the homework. And also when you take the exam. So let's look at this. So we've got 3 rows here with 3 different compounds and 4 columns. The first column is the molecular formula. So I always want you to be able to write the molecular formula from the structure. That's very important. You know, when you're doing chemistry, you have to know what the molar mass is often. And you find the molar mass from the molecular formula. And so you have to know how to derive the molecular formula from a structural formula. So in this case, we have CH3, CH2, OCH3. So the molecular formula, let's see, there's 1 carbon plus 2, 3 carbons, and there's 4 carbons. So it looks like there's 4 carbons. So I write my formula C4, and this is open chain, right? And all the bonds are single bonds. That's what I'm talking, these are all single bonds. So since they're all single bonds, we know that there's 2N plus 2, even though there's an oxygen in there, as long as that oxygen is not double bonded to a carbon, and in this case it's not. Our formula for the ratio of carbons to hydrogens when there's all single bonds is C4H2N plus 2. So that means we have 10, 8 plus 2 is 10 hydrogens, and we have 1 oxygen. Now I could count all the hydrogens too, just to be sure. If I wasn't sure, I could just count them all. And we can do that. There's 3 there, and there's 4 there, that's 7, and 3 more makes 10. So now let's write the Lewis structure. So the Lewis structure, we have a carbon, and then we have 2 more carbons, and then we have an oxygen, and then we have another carbon. And every carbon has 4 bonds, so you can right away draw 4 bonds on the carbons. Every oxygen has 2 bonds, so that's okay. And then we just fill in with the hydrogens, and that's our Lewis structure for this condensed formula. And then next, I want the line structure. So remember the line structure, you start at one end and you draw a zigzag for each, let's see, the terminus, CH3 would just be a dot here. That's like the end of the line. And then we're going to draw a zigzag for this the CH3, CH2, and then CH2. And then that CH2 down here, it's a CH2 because it's connected to the oxygen. And then we have one more line to the CH3. So remember the lines show the bonds. So we have this bond here to oxygen. We have 2 bonds on each side of the oxygen that are shown there. And the CH3 is just the end of the line. So that one looks like that. So I think I'll just work all of these. Now it turns out that all of these are C4H10O. Each one of these is C4H10O. And this is kind of a preview. If compounds have the same formula, remember, but different structures, they're called isomers. So these are all isomers. So this one here, we have a carbon here in the middle. So it already has 4 bonds to it, so there's no hydrogen. So we have a carbon here. And then we have a CH3, a CH3, and a CH3, because we have 3 of those, 1, 2, 3, and then we have an OH. Okay, there's our condensed formula. And then our Lewis structure is going to be show all the bonds, and Lewis structures even show lone pairs if you do it right. So we have C there. So we have 4 carbons. Each carbon has 4 bonds, and each Then we have to add all the hydrogens. So you can see it's very tedious to draw Lewis structures. So we hardly ever draw Lewis structures of organic compounds, condensed structures, and skeletal structures. So lastly, we have CH3, CH2, 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 and then an OH. So I can do that, CH3, CH2. And I can combine these. I'll do 2 CH2s. And then I'll do the last CH2 with an OH attached to it. And then lastly, I'm going to make a zigzag. So I'm going to start here and I'm going to start zigzagging for all the carbons. I need 4 carbons, 1, 2, 3, 4, and then an OH at the end. So I'm going to start here and I go, this is 1, that's 2, that's 3, that's 4. It's 4 carbons. Then I have to put a bond to an OH. So this one looks like that. So you can see that all the structures, whether they're Lewis structures, condensed, or line or skeletal structures, all look different. The other thing, if we're learning how to name these, all the names would be different also. So that's it. That's the worksheet and the lecture on drawing and recognizing organic chemical structures. So I hope this helps you as you go forward. And for those of you who are taking organic chemistry next semester, you will get really familiar with drawing structures this way. So that's the end. So take care, and I'll see you next time. Goodbye for now.